Hey everyone. The next topic we are going to focus on is boundary condition analysis, and so that we don't get a really long video file, I've broken this one up into three parts. So what are our objectives? First of all, we want to review and understand the different types of boundary conditions that you need for a model. All models have to have some kind of boundary conditions, otherwise you can't solve the underlying governing equations. But there are a lot of ways you can mess up your boundary conditions, so we're going to have a discussion in part 2 on some of the problems with ill-posed, improperly configured boundary conditions. And for cases where it's really difficult to come up with good boundary conditions, we are going to talk about a technique called regional to local model conversion that can be used to get around that, to help you come up with some good boundary conditions for your model. And then finally, we're going to review just a few case studies in part 3 that will illustrate some of the things that we talk about. So here are the three main kinds of boundary conditions for groundwater models: both constant head and head dependent, specified flow boundaries, which I'm not sure that we've covered much yet, and then no flow boundary conditions. And we've talked about these a little bit, but we're going to dive into it in more detail. So specified head or constant head boundary conditions, this would correspond to some large water body that has a direct connection to the aquifer, meaning as water moves between the object and the aquifer, there's minimal head loss. So there's not some underlying sediments that have a substantially different hydraulic conductivity than the aquifer, and therefore result in a head loss. And water can go both ways, from the aquifer to the water body, or from the water body to the aquifer. And that is somewhat frequently used boundary condition on groundwater models. A more general class of boundary conditions are what we call head-dependent boundary conditions. And in this case, this would be like a river or lake, reservoir, even a drain, with some intermediate low K layer that does result in some head loss as water moves between the two. We've reviewed like the river package in ModFlow, shown with the diagrams on the right. We can have water gaining river or losing river, and there's some head loss through the sediments. General head boundary the general head package can be used to do this. Now, we often refer to these as sources and sinks. And when we say boundary condition, is that something in the middle or something on the boundary? Well, for the purposes of this discussion, we're more talking about the edges of your model, define your boundaries. And you can have these kinds of objects serve as a suitable boundary condition on the sides of your models. Okay. The next kind of boundary condition, I believe in my intro slide I referred to it as a specified flow boundary. And in the title here I'm calling it a lateral flow boundary. Basically, this is, again, we're talking about what you apply to the edges, the outer edges, the boundaries of your model. And one option is to have a specified flow, typically an inflow. And this is really common in alluvial aquifers and basins that are adjacent to a mountain range, as shown in the upper right figure here. Where you have runoff in the spring coming from the mountain range, snow melt, or runoff through a thin superficial layer of soil that then goes into the edge of your basin as a form of lateral flow. And you could simulate this with a set of, you could select the cells along the edge of your model and put a well, a series of wells, where the total amount of water going into the wells represents the amount of water that you've decided you want to introduce. Or you could select those same cells and have a larger value of recharge coming through those cells. So either of those methods will get the right amount of water in. Of course, the trick in this is determining how much water you want to put in. The model shown on the left, we're going to revisit this one in part 3 of our discussion. This is a groundwater model I helped build in Sacramento, California. And this red boundary here is the actual boundary of the groundwater model. But then these basins up here, 1, 2, 3, 4, 5, 6, 7, that are just beyond the edge of the model, we ended up using a runoff model, external to mod flow, to calculate, based on snow melt and precipitation, how much water we believed would seep into the superficial soils and then eventually migrate through the boundary into the model, and then we made those lateral flow or specified flow boundaries. So you do see this occasionally, most typically when there's a mountain range next to your model. Okay, now let's look at a series of no-flow boundary conditions, the most simple of which would be a physical barrier of some kind. In the example shown here, we have a bedrock outcropping on the left side of the model. We're simulating flow in these, again, in this basin. The bottom of the basin is bedrock, and then that eventually outcrops on the left side, so that becomes a no-flow boundary. How do you apply a no-flow boundary? You don't do anything. In mod flow, as is the case with most numerical models, the default boundary condition is a no-flow boundary condition. So if you don't do anything, it is no flow by default. So you really don't have to do anything. And so that's fairly simple. So that's the most straightforward one. I mean, it could also be a really low permeability fault. Could conceivably be a no-flow physical barrier, but some sort of bedrock outcropping, or just an extremely low permeability unit that differs by several orders of magnitude in hydraulic conductivity would be another kind of physical barrier. Another one, which we've talked about a little bit, but I want to make sure you clearly understand, is a groundwater divide. So let's suppose that we have this hypothetical site here. This is a cross-section through the site. We have rainfall, which causes recharge, that causes the groundwater table to mound. It drains to the left and the right to these rivers or lakes or whatever these are. And so some of the water is going to flow to the left, some of the water is going to flow to the right, and somewhere here in the middle, corresponding to the kind of the high point of that water table, is going to be what we call a groundwater divide. It basically is just a line marking the division of these flow directions. And if you could imagine, since there's no groundwater that flows across that line, you can make that the edge of your groundwater model and treat it as a no-flow boundary. And you could either model the region on the left of that or the region on the right and use that groundwater divide as a no-flow boundary. You have to be really careful with these. Make sure they are located some distance away from where any significant changes are going to be made to the model. For example, if you used a groundwater divide as a no-flow boundary, and then you simulated a scenario in your predictive phase where you put some new pumping wells close enough to that groundwater divide to change the shape of that water table surface, then the assumption you made to place that groundwater divide there is no longer valid. So just be really careful with that, and remember that when you're using this type of boundary condition. A similar type of boundary condition, no flow condition, is called a parallel flow boundary. In this case, let's suppose, for the sake of argument, that if we look at contour the water levels from our monitoring wells, we come up with these head contours of what the ambient groundwater flow conditions are, and the water is going to flow perpendicular to these lines. And so if we were to draw a line parallel to those flow directions, once again, there's no groundwater crossing that line, so that can be used as a hypothetical no-flow boundary. It's kind of like a groundwater divide, but a little bit different scenario. And the same caveat applies here. Be really careful when you go into predictive phase that you don't change the conditions so substantially that parallel flow, no flow condition is no longer valid. So let's put these two together. Here's an example of a site. We have a river meandering around, and we want to develop a local scale model to simulate this industrial plant. In this section, between this, where the industrial plant is located, in this section between the rivers, you're going to have accumulation of groundwater due to recharge, and that's going to cause a mound. And somewhere in the middle of this line, there's going to be a groundwater divide where the groundwater goes this way or this way. And then if it's flowing from the groundwater divide to the river, then perhaps you could put in parallel flow boundaries. And this would be similar to the Fremont River exercise we did in class for some of our exercises. So again, a groundwater divide here, parallel flow boundaries here, and then this river would either be the river package or a specified head boundary condition. And now you have boundary conditions for this site. Another option would be to just extend your model boundaries out to the river all the way around, and then somewhere in here there could be parallel flow boundary as water goes. Let me see if I can annotate this a little bit. You could have water flowing in this direction, so that could be a parallel flow boundary, and then water flowing in this direction. So you could have no flow boundary here, and then a head dependent boundary condition here, and model the larger site as well. Both of those, I think, would be a reasonable way to approach this topic. So that concludes a quick review of the different boundary condition types.